Okay, I'm unmuted now. Is it actually just, oh, it's just D. Okay. And so you're not directly comparing the distributions to each other, you're comparing the gradient flow to distributions to each other. And so, okay, so as I was talking about, we create our spatial distribution with this kernel function. They use a radial basis function. How you shape that, and even the choice of the kernel function, like in general, is very much a design choice. Some papers use like a square, some use like a uniform distribution, some use like a Gaussian. It's a user choice. In this case, they're and you can kind of use it as also a metric for exploration versus exploitation. In this case, where like if you have a sort of a tighter basis function about your point, you might sort of favor more of these like high density regions. As you spread that out, you might get away with having a more sort of explorative type behavior.
So this is like your coverage area, basically.
Yeah. Like, yeah, I think that's like, you can imagine if you, like if it was a camera and you were looking at them, that's your that little circle is what you're observing of this landscape. Then yeah, that would be the case.
Yeah, so in the case where you're modeling every single point in space here is having some information, then I would imagine this distribution has to change dynamically as a function of what you've already visited.
No, the target distribution does not change dynamically. It's held static.
Mm-hmm.
In this paper,
I haven't seen any that have a dynamically changing target distribution, like as a function of like you observing that search space.
I remember how quickly the planning is here, but you could update your target distribution and like, I mean,
Yeah. You could do like an NPC style.
Well, okay, yeah, you could do an NPC style, but like, I think you're asking more like, can you actually bake this into your like environment dynamics and actually integrate when you observe this map? How does it change?
An NPC would be ideal if you could capture the fact that revisiting an area that was originally high information may not be high information.
Yeah, I mean, I guess I would say that that's sort of implicitly captured by the fact that you are, like, it's just like, I guess, because they're proportionally visiting areas that have high density more, that behavior is kind of naturally captured.
I think it would also make it hard to do in a dynamic environment because, like, maybe some point has like a high desirability of visiting, but then if it changes, you kind of have to like average out. Like if you really want to visit this point now and then you visit it and it becomes low probability,
Mm-hmm.
then you know,
Mm-hmm.
so you'd have to like have some.
Yeah.
You wouldn't be able to like plan your trajectory off.
Yeah.
or maybe that the target distribution represents kind of places you want to visit. Like it does get updated, but not like as quickly as you're replanning. Maybe it's updating like every 10 minutes as opposed to like every.
Mm-hmm.
Yeah, I think maybe if it keeps on updating, then going like,
Yeah.
keep on
And your trajectory is capturing like visiting all of the high probabilities or high desirability.
Mm-hmm.
But maybe those distributions do change, but not drastically. So maybe it's like a combination of like time. Complicated.
But this paper specifically says they don't have that.
Yeah, no, yeah, this paper does not. It's I have not encountered any that do have like an NPC style. Like, but like that's a pretty natural like extension. Like that's yeah, I don't think that would be like, I think in any real like implementation of this, if you're like trying to do coverage planning or something, that would be a pretty like natural extension.
So what do you mean by exploitation in this context? Because it seems like no matter what's happening here, it's still trying to just match this distribution. That's the only
exploitation in that it's spending more time in high density regions.
Okay. Is that actually what we see with the like distributions that these end up giving? Like, do we?
Like if you, I get, be good if I didn't also, but if you imagine like in this case, because we have this smaller kernel, those basis functions are going to be tighter and proportionally cover like a smaller given amount of areas. So this is with respect to creating this basis function and with respect to the dynamics of the system, you're getting more, like this is what proportionally, given those constraints, you would end up with. Whereas if you have this larger sort of scope of your basis function in that case, then you have like a much bigger circle. And as you add basically each of those up for each of the nodes, you would get more like you're just spatially covering more areas. You're getting more exploration.
Is it correct intuition that
At least
if
it's
you
my
have
intuition.
a smaller radius kernel, like essentially you have like a smaller covariance, so you have like a peakier distribution.
Mhm.
And so the peakiness is going to try to match with the peakiness of the landscape. And so you'll
Yeah.
go to like a higher peak region. Whereas if you have like if you have a lower covariance or larger covariance, then you'll go to less high probably or high.
That seems like a
like
fair takeaway.
I guess what I'm asking is like, if, so when you say exploitation here, you're saying that the one on the left, it's staying within this high density region because its kernel is very small and it can't explore very much area in the amount of time that it has, so it's going to explore this high density area. But if you were to normalize by like the amount of area that each one of these can sweep out over time, would a large kernel bandwidth be a bad thing? Like it can still search. There's nothing that's stopping it from searching high density areas more frequently. It's just also at the same time searching low density areas.
Yeah, no, I like I'm not, and I don't think the paper is either like saying any one of these is better than any other. I think they're just trade-offs. Like it's a tuning parameter for the type of behavior you want in your system.
Okay. But is this a parameter that you get to really choose? Like if this is your camera field of view, then
Yeah, it could be. I mean,
For like the height.
yeah, I mean, in a camera case, like, I mean, there could be many things. Like if you have a fixed camera, like if you look at like a plane obliquely, you're going to stretch out your distribution, so you could change the covariances from that. You could change, like as you physically get closer, you might like bump up your peak effectively, to denote that like as you get closer, you're getting more information, but maybe your overall like sort of I guess uniformly the covariance would shrink. But yeah, that so I think it's reasonable in those cases to play around.
does
And
this
like
method allow for the base the kernel to be like some parameterized function?
yeah, no, there's this paper only went with RBFs, but there's others where they use like a still a circle, but it's uniformly like, so they like basically everywhere within this kernel distribution is treated equally. There's some that use a square, some that use like a trapezoid.
I'm
Some
saying, if can you does this method extend to like parameterizing the kernel and then having that also be an optimization? Like if
I see what you're
allow it
saying.
to fly upwards in order to see.
I haven't seen any work. I want to do that.
Oh, okay. All right.
But yeah, like particularly in the case of what, or like your view planning and you're looking at some distribution on a plane, like if you can optimize for the covariance values, for example, you can basically figure out like in what orientation does my camera need to be to get like this sort of oblique look and get like maybe like stretch out your distribution so you sort of cover this full area. But yeah, I think that's a pretty good research direction to go with this type of stuff.
I think I want to expand a little more on the exploration discussion here because in certain cases, I could see exploration as referring to trying to get to specific parts your entire space, not just covering the entire space.
Mhm.
Like here, for example, with the heat map here referred to how high your uncertainty was, and the darker was higher uncertainty, then I would think it'd be more explorative to actually take the trajectory to the way left rather than exploitative. And moreover, like consider moving around in like an area with a lot of obstructions, like a building. There's something called frontier exploration where you're just trying to, you're trying to essentially explore the frontiers of your known environment.
Mhm.
And in that case, you would have high density areas that you want to move in throughout this much larger space. So
I mean, like in your frontier exploration case, inherently your target distribution is changing.
yeah, but I'm
So,
just
like-
saying, like at any instantaneous point in time, you have some known part of your environment and some unknown part of your environment.
Mhm.
So when you want to have, I guess in this case, like high district, like high, I guess your distribution kind of centered on those frontiers. And
Yeah,
what you
I
call
mean,
that I guess exploration in that case.
But I think what you're saying is it's how you're interpreting distribution.
Yeah,
Right? But like if you just like, here's some shape that I either focus on the darkest region or spread out, like that's what the exploration is. But I think your example was like maybe a little specific exploration. So you want to do like the inverse of what they're
Yeah,
saying,
yeah.
but to your-
So exploration becomes the, I guess the exploitation is referred to here, yeah.
I think it's never. I think. Correct me if I'm wrong, but basically they're just using these like distributions, like the heat map is just an objective.
Yeah.
Right, that's kind of like time is somehow implicit to like.
Yeah.
Like how much time you spend in each
Yeah.
area.
Yeah.
Also,
So in practice, going on if there's no questions. Okay. In practice, they solve this with iterative LQR, where they're trying to minimize the difference in the vector in the flow vector field of their spatial distribution and this target distribution. And basically they claim that by doing this sort of flow matching measure, it improves. So, okay, in this paper, they propose 3 different metrics. There was a Fourier-based one, a Sinkhorn divergence, and a Stein divergence. And I think in this case, because they use the Sinkhorn, they're able to use a optimal transport-based metric in lieu of the KL divergence. And this can lend better, basically do more to non-smooth target distributions. And then the Stein divergence is also robust to non-normalized target distributions. And so just a few experiments. So in this case, they're using the Sinkhorn. And in this case, if you have a distribution like this, where you're trying to sort of, in this case, like perfectly uniform across this space, but not smooth. This is where like the Sinkhorn with the ability to have this type of behavior is like outperforms the existing methods, I guess, quite a bit. They have a few other cases over here. They're going through a few different methods. And I think sort of across the board, they're always performing better given the same route time and the same dynamics.
Sorry, 'cause I
Hmm.
did you
Mhm.
okay, so how the framing ergodic coverage as a flow matching problem, like do you think that was kind of obvious or kind of like really elegant?
Didn't strike me either way. Like I thought the fact that it enabled you to use like other metrics that were like previously weren't really computationally tractable within the method, I think it enabled, that was like the biggest thing I think it did. I think it in of itself, like it seems like a pretty natural way to do it to me, but
So the main assumption here is assuming
mhm.
assumption. How do you get this? Have some like known dynamics. How do you get this ground gradient?
Like for the target distribution or for,
So because if this
yeah, I guess they're assuming that, yeah, you're given some knowledge of your field, like in maybe in a case like this, you're given some I don't know, Gaussian model of your or Gaussian process of your search space based on some prior observations. Or like maybe in a planetary landing case, you have an orbiter that's has some prior observations of a potential landing sites. And as you're descending down, you're like sort of sweeping your sensor to look at these potential landing sites based on those prior observations. As one example, I mean, they also others, they just give like in this case, I imagine they just gave like a absolute like vector graphic to their algorithm so they can get like a ground truth. Go.
Intuition about what the field looks like for this? Is it just pushing you onto the shape?
That would be my guess. I'm not certain.
This flow matching, in the map here, is this essentially saying, if we go back to the other figure, at each iteration point, you're taking where I guess the state currently is at that point in time, and essentially just like iterating it in the exact direction of the flow at that particular point.
That's my understanding.
And it's projected, I would assume, is it projected onto a feasible constraint space?
Yeah. So the way they subject to like a feasible constraint space, they basically iteratively like solve the LQR problem, roll it out, get the trajectory, apply it through this flow matching process, and then basically it shifts towards like that direction, and then they do this iteratively until. Sorry, say the first part again.
Like in standard flow matching, I think they use like this linear interpolation for the
Mhm.
objective for the
Mhm.
mouse.
Mhm.
So you have, like, source distribution. Like I'm a little.
Like I'm familiar with like regular flow matching.
Yeah, me too.
I'm just trying to understand like how they take those ideas or methods.
So in regular flow matching, you have the source and then you have a target distribution, and you're trying to obviously push the get the vector field, right? And so you would just take a linear line and then push the Gaussians or whatever. And so I'm wondering how.
Yeah, my understanding, yeah, is like the iterative step, yeah, would be like just a linear push. Like as like you
understand the connection. Because you would sample random points on that linear line at every time step, and then that's how you do the MC on the vector field.
Mhm.
Just that's how, yeah. So how are you ensuring that process aligns with that?
I guess I'm not sure.
It's being interpreted as a linear interpolation between probability density functions.
Yeah. Yeah, I think it's like source, target, line, sample that line a bunch of times at every time, and then you do the MC on it. That'll like where which direction to go to. So even if it's bimodal, you have sample the lines, and you kind of learn the direction to learn it every time. I'm wondering how that process is like.
I don't know, maybe that's where the ergodic information.
What is flow matching better than gradient? We have a ability to like a flow gradient.
It's minimize one function. They're trying to learn the underlying. They're trying to learn those underlying probability distributions. The way they do it.
I feel like here they.
Well, to learn flow matching, you do gradient descent, but you learn a velocity field, which is like where that linear interpolation comes from. Like, oh, Like, where is a particle from this distribution? Like, how does it travel to that distribution? And like by interpolating, eventually you build up like a density at each time step of like the velocity path. But it is like also unclear to me exactly how
Like this.
they do it here.
Source, target, and then at every time step you draw like a line or whatever, and then linear interpolation, which there's theory for it in the And then at every time step along this line, you would like take that time step and figure out which direction the vector field's going. You kind of learn this probability is versus vector field. So yeah, I'm just wondering how this process went.
Accept that they.
Sure.
We're matching technique to get this.
Yeah, they have like I can send this. So they have Jupyter notebooks to go along with this if you want to poke around and see what they're doing. But yeah, okay. Yeah, so they also demonstrate you can do this in FreeDOF. I think it'd be much more interesting if you did this in 6DOF, where you actually like aren't just like visiting like an area as like making your spatial distribution, but actually what you're observing in that area is how you build up the distribution. But I did think this is a pretty slick way of demoing it, where they actually drew like on a whiteboard to demonstrate how you can like have a very non like nice distribution, and they're which I'm pretty sure they're just planning like a 2D double integrator for the end effector of this manipulator, and then not doing like full 6DOF stuff. But
I'm way faster.
I'm way faster.
Isaac is not impressed.
But yeah, I mean, I think in the sense of like you're like proportionally visiting these areas based on how they're drawing, I thought that was impressive. They're not just so as like as he like I think he draws the orbit stops and then he starts it. Like he's not like dynamically adding crap on, and it's I don't think so.
Like it was
Like here, I'll he's gonna start writing, I think, with the red marker.
Oh, I see.
Yeah, like that's the input.
I mean,
Is-
theoretically, I don't think it would be very difficult for you to real time.
Yeah.
Just
Yeah.
Have it running constantly.
Yeah, do they say
Because
computation?
I don't know how fast he says it.
Yeah, like
They even said you could
One-
probably replan online, so.
Well, flow matching is like notoriously fast too. So you just
I guess I've my thoughts on, obviously I come from a heavily SCP background. So my like how I'm interpreting this is how I can implement something like this within SCP. I think one of the limitations they have is they're with this ergodic cost, they only put these like RBFs on their nodes, and ergo they have like a ton. There's like 200 nodes in their problems, which is not, I mean, like they're doing this with very simple dynamics and a simple search space. So I think it's feasible then, and they have like a nice JAX backend. But if you, rather than like just summing up all these things, if you could truly like basically pose this ergodic cost as like a true integral, not just a summation over your nodes, that like within using the way that we handle our discretization and integration, then you could get away with much less nodes, and rather just promote basically the true integral of sweeping this kernel function across your target distribution. And I think also would be probably more straightforward in terms of enforcing constraints. But yeah, that was it. That what, sorry? I haven't seen any that are like obstacle avoidance, like baking that in to your probably as one example. I think another more interesting one is not just like not just like the position of yourself as making your spatial decision, but like if you have like a planner environment, you have like a full 6DOF vehicle with a sensor that's like rigidly mounted. If you imagine like you take sort of the bore set of that sensor, you project it down to the ground, and this is the point you're actually like sort of swooping around and planning for, but you're planning like a 6DOF, true 6DOF, like dynamically visible trajectory for this robot to ensure you're optimally, I guess, sweeping around that sensor footprint. I think that's something that would be very challenging to do in an LQR fashion that I think our methods would lend pretty nicely to.
I think I shared with you a paper. This was like best paper at RSS 2023, time optimal ergodic search.
Mhm.
They do have obstacles for a drone. So there's, I guess, some work on doing ergodic search in cluttered environments. I don't know if they have any like attitude control for this drone. Maybe it's just like planning in 3D, but
Mhm.
there's at least some work on constraints, or at least obstacle constraints.
Mhm.
To you.
Yeah, I think I haven't seen any that dealt with like attitude in addition to position.
What about the 3 degree of freedom?
Oh, I would say 6. Like it's yeah. Like in this case, it's just moving, like it's a point mass moving around.
It's not like a coverage planning thing.
It's like they kind of phrase it like that, but the coverage is coming just from you occupying that space, not so much you like.
There's no perception.
There's no perception exactly, and I think, yeah, I think incorporating that would be nice.
Follow this. But like, if you had attitude, for example, you would have a distribution safely of your attitude. So could you not just have like a subset of the state constrained by this, or determined by the ergodic formulation? And like
So you're saying like compute like separate it all, computer like a 3DOF position, and then add in
like merge it together.
two step.
A subset of your state is constrained by.
I mean, I would probably express the like, in the sense of blending case, I would like when you project your bore sight down to this planar space, I would express mu and sigma being mu the mean, sigma the covariance of this distribution of your sensor footprint hitting the ground as states in your problem. And like ergo optimization variables, to your point of view.
I'm just saying, like, if that becomes your goals, and then it seems like they're constraining at least the dynamics.
But is that not already what they're doing with the velocity? They don't have ergodic constraints on the velocity, right? Or ergodic cost on the velocity, right? So, and they're already picking only like a subset of the state vector that they need to do coverage with.
I guess my point is, like same point, but if you solve that minimization problem that you had a few slides back, subject to the dynamics and whatever other constraints you want, but the objective is only evaluated over the positions or the position of the foresight vector. I think that would, like, wouldn't that just work in this formulation?
I guess I'm not understanding. So are you decoupling position and attitude?
But can you go back to the optimization?
You see, like, system has certain states. It could be like 50 states, sake of argument, but your the distribution that you want to do ergodic coverage over, like that doesn't need to be over 50 states.
No,
Right? Like it could be a subset. Is what you're saying?
Like your state could be like, as you pointed out, you have position, velocity in your state, but this is probably only done over position.
Yeah. So
So similarly,
you define the distribution.
So similarly, you could tack on attitude and angular velocity onto your state, and then I think it would just directly fit into this formulation.
Yeah. I guess in that case, I would guess the parameterizing your your kernel function as like actual like states in your problem, and have like basically the position of that, like of that projection, and then the covariances associated with that projection. That's like what I would do the like ergodic planning over, but that's like, yeah, I mean, you're right in the sense that, yeah, I'm just choosing a different state space to do my ergodic search over, rather than the position, not directly over the position of the vehicle, but over the position of like its boresight vector projected down to the,
But it's a functional state.
yeah, it's a function of state. So like implicitly, this will roll all the way back through the rest of the states. But yeah, the ergodic search is not over like all of it. It would just be over that.
So as they've done this in the paper, this Q matrix for the norm, like that only has components for the position.
XY
and
position.
zeros for velocity.
Yes.
Okay.
Yeah, they're only grabbing 2 DOF position.
Yeah, so in that case, I feel like doing what you were describing, like the 6-DOF planning where you're looking at it. And it's the boresight vector that you care about the distribution of. I feel like that directly fits in.
Yeah.
I mean, obviously that's like a very non-linear optimization, but they just know that I also which is like.
Any other questions?
I do think extending it to like times interesting. I don't know. That feels like something that would lead to an intractable problem, but
I think like Mark, I have been kind of mentioned this a while back, like if you're doing like search and rescue, kind of like if this what you're applying this to search and rescue, like the other reasons I need to visit, like